CompTIA SecurityPlus Objective 2.3 asks you to explain various types of vulnerabilities. A vulnerability is a weakness that could be abused to affect confidentiality, integrity, or availability. The objective spans application flaws, operating system weaknesses, web vulnerabilities, hardware and firmware problems, virtualization, cloud-specific exposure, supply chain weaknesses, cryptographic failures, misconfiguration, mobile device weaknesses, and 0 days. Do not treat every vulnerability as simply an unpatched system. Some flaws come from unsafe design, memory handling, race conditions, broken trust, weak configuration, unsupported hardware, or incorrect use of cryptography. Use a repeatable exam process. First, identify the vulnerable layer. Second, identify the condition that makes exploitation possible. Third, determine the likely impact. Fourth, select the control that addresses the root cause. Input validation helps injection risk, but it does not replace an end-of-life device. Patching fixes known code defects, but it cannot correct every unsafe business configuration. Throughout this lesson, connect layer, weakness, impact, and mitigation. Separate three related ideas: vulnerability, exploit, and exposure. A vulnerability is the weakness itself, such as missing bounds checking, a default permission, an unpatched driver, or a flawed update process. An exploit is a technique or code that abuses the weakness. Exposure describes the reachable condition that allows a threat to interact with it. A vulnerable service isolated from all untrusted access may have lower immediate risk than the same service published to the internet. Risk also depends on likelihood and impact. A scanner can identify evidence of known weaknesses, but the result still needs validation and prioritization. False positives are possible, and two systems with the same vulnerability may carry different business consequences. On the exam, avoid calling the malicious payload the vulnerability. The payload is part of an attack. The weakness that permits execution is the vulnerability. Controls may remove the weakness, reduce exposure, prevent exploitation, detect activity, or limit impact. The strongest answer usually addresses the specific condition described in the scenario rather than merely adding a general security tool. Application vulnerabilities arise from design, implementation, dependency, and configuration mistakes. Untrusted input may reach an interpreter. Memory may be handled without correct boundaries. Multiple processes may access shared data without synchronization. An update mechanism may trust a compromised source. An application may run with excessive privilege or reveal sensitive information through errors and logs. Secure development reduces these risks across the software lifecycle. Threat modeling identifies dangerous trust boundaries before coding. Code review and static analysis inspect implementation. Dynamic testing evaluates running behavior. Fuzzing sends unexpected input to reveal crashes and unsafe states. Dependency analysis finds vulnerable third-party components. Patching and secure configuration protect deployed systems. Least privilege limits impact when prevention fails. For exam scenarios, trace the data. Where does input originate? Which component processes it? What privilege does the process possess? What state or resource can be changed? That path usually reveals whether the best answer is input validation, safer memory handling, synchronization, signed updates, patching, or another focused control. Memory injection places or executes malicious content inside the memory space of another running process. An attacker may allocate memory, write code or instructions into a trusted process, and redirect execution. Running inside a legitimate process can inherit its access and make malicious activity harder to distinguish from normal behavior. Memory injection is a broad concept and can appear after an attacker has gained some ability to execute code. Defenses include patching the initial weakness, least privilege, application control, exploit protection, behavioral endpoint detection, and memory protections provided by the operating system. Monitoring may look for one process opening another with unusual rights, writing to executable memory, or creating a remote thread. On the exam, distinguish injection from a simple malicious program running independently. The key clue is abuse of another process or its memory. Also, separate the technique from the original vulnerability. A phishing attachment might deliver malware, while an application flaw enables execution, and memory injection helps evade detection or access another process. Read the chain and identify the layer the question actually asks about. A buffer overflow occurs when a program writes more data into a memory buffer than the buffer was allocated to hold. The extra data can overwrite adjacent memory, causing a crash, corrupting information, or redirecting execution. Stack-based and heap-based overflows affect different memory regions, but the exam-level pattern is the same. Input exceeds a boundary because the program fails to enforce size limits. Defenses begin with secure coding and bounds checking. Memory-safe languages reduce many manual memory management errors. Compiler and operating system protections add layers. Stack canaries help detect overwritten control data. Data execution prevention makes designated memory non-executable. Address space layout randomization makes useful memory locations less predictable. Fuzz testing can reveal crashes before release, and patching corrects known vulnerable code. No single mitigation is perfect, so layers matter. In a scenario, clues such as oversized input, overwritten memory, unexpected crash, or arbitrary code execution near a fixed-length field point toward buffer overflow. Choose remediation that corrects memory handling, rather than only blocking one observed payload. A race condition occurs when security or correctness depends on the unpredictable timing of multiple operations. Two threads or processes access shared data, and the result changes according to which one runs first. Each step may appear valid by itself, but unsafe interleaving creates an unexpected state. For example, two requests may both confirm that a balance is sufficient before either request subtracts funds. A race can lead to duplicate actions, corrupted data, bypassed authorization, or privilege changes. Controls include locks, semaphores, atomic operations, transactions, and careful synchronization. The goal is to make a critical sequence behave as one protected operation. Testing must include concurrency and unusual timing, because the flaw may not appear during normal single-user tests. On the exam, look for words such as simultaneous, timing, shared resource, threads, or inconsistent result. Do not confuse a race condition with simple performance delay. The security issue exists because another operation can change the relevant state before the first operation safely completes. Correct the synchronization and transaction design rather than relying on users to retry. Time of check and time of use, often shortened to TOC and TOU, is a specific race condition. A program checks that a file, permission, path, or resource is safe. Before the program uses it, an attacker changes the state. The program then acts on something different from what it validated. Imagine an application checking that a temporary file belongs to the current user. An attacker replaces the file with a link before the privileged application writes to it. The check was correct at that moment, but the later use is unsafe. Defenses include atomic operations that combine validation and action, secure file handles that continue referencing the validated object, locking, safe temporary file creation, and revalidation when appropriate. Reducing privilege also limits impact. On exam questions, identify the gap between validation and action. If the state changes during that gap, think time of check versus time of use. The best fix is not simply to check faster. The operations must be designed so another actor cannot substitute or modify the resource between them. A malicious update abuses the trust organizations place in software distribution. Attackers may compromise a developer workstation, build pipeline, update server, signing key, repository, or third-party component. The resulting package reaches customers through a process that normally indicates safety. Because updates may run with high privilege and deploy broadly, one compromise can create large impact. Defenses protect the entire update chain. Secure development and build environments, separate duties, protect signing keys in hardened hardware, review code and dependencies, verify digital signatures, use reproducible builds where practical, and monitor release activity. Organizations receiving updates should validate signatures, stage deployment, test behavior, maintain rollback capability, and watch for unusual network or process activity after installation. On the exam, a legitimate update channel delivering harmful code points to a malicious update or supply chain weakness rather than ordinary phishing. A valid signature proves that a key signed the package. It does not guarantee the build process or signing key was trustworthy. Trust must be protected from source code through deployment. Operating system vulnerabilities affect the platform that manages memory, processes, devices, identities, files, and applications. Weaknesses may exist in the kernel, drivers, services, system calls, permissions, or default configuration. Because applications rely on the operating system, a successful exploit may enable privilege escalation, credential theft, persistence, security control bypass, or broad data access. Reduce risk through timely patching, secure baselines, removal of unnecessary services, least privilege, application control, secure boot, driver restrictions, endpoint detection, and supported operating system versions. Segment critical hosts and protect administrative interfaces. Configuration drift matters. A fully patched system may remain vulnerable when permissions or services are unsafe. On the exam, look at the affected layer. If a flaw in a driver allows a normal user to gain kernel-level privilege, that is an operating system vulnerability and privilege escalation impact. If only one web application mishandles input, the vulnerable layer is the application. Choose controls that address the platform while recognizing that patching, hardening, and privilege management work together. Web vulnerability analysis starts by following data across trust boundaries. A browser sends a request to a web server. Application code processes parameters, cookies, headers, uploaded content, and identity state. The application may query a database, call another service, and generate output returned to the browser. Untrusted input becomes dangerous when it reaches an interpreter without the correct handling. Output becomes dangerous when attacker-controlled content is returned without context-appropriate encoding. Sessions become vulnerable when identifiers are predictable, exposed, or not invalidated. Authentication and authorization are separate. Proving identity does not guarantee permission for every object or action. Core defenses include server-side input validation, parameterized queries, output encoding, secure session management, least privilege for service accounts, patching, logging, and testing. A web application firewall can add protection, but should not replace secure code. On the exam, identify where data changes meaning. Input reaching a database interpreter suggests injection. Content reaching another user's browser suggests cross-site scripting. The next slides will compare those specific flaws. Structured query language injection, or SQL injection, occurs when untrusted input changes the meaning of a database command. A vulnerable application may build a query by combining fixed text with user input. An attacker supplies characters that escape the intended data field and add new query logic. Depending on permissions, the result may reveal records, bypass authentication, modify information, or delete data. The primary defense is parameterized queries, also called prepared statements. Parameters keep data separate from command structure, so input cannot become new SQL syntax. Server-side validation adds another layer, but validation alone should not replace parameterization. Use a least privileged database account. Avoid detailed error messages, patch frameworks, log unusual queries, and test with code review and dynamic tools. A web application firewall may block known patterns, but secure code addresses the root cause. On the exam, look for database errors, altered query logic, authentication bypass, or characters inserted into an input field. SQL injection targets the database interpreter. Choose prepared statements over merely filtering a few dangerous characters. Cross-site scripting, or XSS, allows attacker-controlled script or active content to execute in another user's browser within the context of a trusted site. Stored XSS saves the payload in the application, such as in a comment or profile, and delivers it to later visitors. Reflected XSS returns input immediately in a response, often through a crafted link. DOM-based XSS occurs when client-side code handles untrusted data unsafely and modifies the page. Impact can include session theft, page modification, fraudulent actions, or credential capture. The strongest defense is context-aware output encoding, because content inserted into HTML, attributes, script, and URL contexts requires different handling. Sanitize allowed rich content, use secure frameworks, apply a restrictive content security policy, protect cookies, and test both server and client code. Input validation helps, but output encoding is central. On the exam, distinguish XSS from SQL injection. XSS executes in a browser and targets users. SQL injection changes a database command on the server. Compare SQL injection and cross-site scripting by following the interpreter. In SQL injection, attacker-controlled input reaches the database interpreter and changes a query. The immediate target is server-side data or authentication logic. In cross-site scripting, attacker-controlled content reaches a browser and executes as script in the trusted site's origin. The immediate target is the user's session, page, or browser actions. Both begin with unsafe handling of untrusted input, but the primary controls differ. Use parameterized queries for SQL injection. Use context-aware output encoding and appropriate sanitization for cross-site scripting. Least privilege limits database damage, while content security policy can limit browser script execution. Consider a search box that causes a database syntax error. Suspect SQL injection. Consider a comment that displays a pop-up to every visitor. Suspect stored XSS. A web application firewall can reduce either risk, but it is a compensating layer rather than a substitute for secure code. On exam questions, identify where the attacker's content is interpreted and who or what experiences the impact. Hardware vulnerabilities exist in processors, memory, storage devices, management controllers, interfaces, and physical components. Some are design flaws that software cannot fully correct. Others involve insecure debug ports, weak random number generation, side channel leakage, counterfeit components, or physical tampering. A processor flaw might allow information to leak across isolation boundaries. An insecure management controller may provide access below the operating system. Hardware issues can have long replacement cycles, so risk may persist even after mitigations are available. Controls include trusted sourcing, inventory and lifecycle management, physical protection, firmware and microcode updates, hardware-backed attestation, secure configuration, and replacement when fixes are insufficient. Segmentation and workload placement can reduce impact while remediation is planned. On the exam, identify whether the weakness is below the operating system. If a flaw remains across software reinstalls or affects the processor's isolation behavior, consider hardware or firmware. A patch may sometimes deliver a microcode mitigation, but it does not change the category of the underlying weakness. Match the answer to the vulnerable layer and the practical remediation available. Firmware is low-level software that initializes and controls hardware. It exists in system boot firmware, storage controllers, network equipment, peripherals, mobile devices, and embedded systems. A firmware vulnerability can provide persistence below the operating system, making detection and removal difficult. Reinstalling the operating system may not remove malicious firmware. Weak update validation can allow unauthorized images, while outdated firmware may contain known flaws. Defenses include authenticated and digitally signed updates, secure boot, measured boot, a trusted platform module for attestation, protected update keys, firmware inventory, and vendor-supported versions. Restrict administrative access to device management interfaces, and verify updates through trusted channels. When firmware cannot be updated safely, replacement may be necessary. On the exam, look for persistence that survives disk replacement or operating system installation, compromise during boot, or a vulnerable device controller. Secure boot verifies that approved components load, while measured boot records evidence that can be evaluated. These controls are related but not identical. Protect the chain from the first firmware instruction through operating system startup. End-of-life hardware has reached the point where a manufacturer no longer sells, maintains, or fully supports the product. Security updates, replacement parts, compatibility testing, and technical assistance may disappear. The device may continue functioning, but risk increases as vulnerabilities accumulate and recovery options shrink. End-of-life creates both security and availability concerns. A failed component may be difficult to replace, and a newly discovered flaw may never receive a fix. The preferred control is lifecycle planning and timely replacement. Maintain an accurate asset inventory, track support dates, budget migrations, test replacements, and securely dispose of retired devices. If immediate replacement is impossible, isolate the device, restrict management access, remove unnecessary services, monitor closely, and document the temporary exception with an owner and deadline. On the exam, distinguish hardware lifecycle from a single missing patch. If the vendor has ended the product line and parts or updates are unavailable, replacement is usually the strongest long-term answer. Compensating controls reduce exposure, they do not restore manufacturer support or eliminate operational fragility. A legacy system is older technology retained because an organization still depends on it. It may support a critical application, specialized device, data format, or business process that is difficult to replace. Legacy does not always mean unsupported, and unsupported does not always mean legacy, but the conditions often overlap. Risk comes from obsolete protocols, limited patching, scarce expertise, weak authentication, incompatible security tools, and dependencies that make change dangerous. Begin with discovery and dependency mapping. Determine what business function the system provides, which data it handles, who connects to it, and what would break if it changed. Then isolate it. Restrict access, remove unnecessary connectivity, monitor activity, maintain tested backups, and build a migration plan. Modernization may require data conversion, application redesign, parallel testing, and staged retirement. On the exam, avoid assuming that a simple patch solves a legacy dependency. If the scenario emphasizes an old critical application that cannot run on a supported platform, segmentation and compensating controls may be immediate steps, but migration or replacement remains the long-term objective. Virtualization places multiple workloads on shared physical resources through a hypervisor. The attack surface includes the hypervisor, host operating system when present, management plane, virtual networks, images, snapshots, shared storage, and guest systems. Virtual machines provide isolation, but that isolation depends on the security of shared layers. A compromised management account can control many workloads. An insecure template can reproduce the same weakness across every new instance. Old snapshots may contain credentials or sensitive data. Unmonitored east-west traffic can allow movement between virtual systems. Controls include patching and minimizing the hypervisor, separating management networks, requiring strong authentication, applying least privilege, protecting templates and snapshots, encrypting storage, and monitoring virtual network traffic. Keep host functions limited and avoid unnecessary software on the virtualization platform. On the exam, identify the shared dependency. A flaw in one guest usually affects that guest. A flaw in the hypervisor or management plane may affect many guests. Virtualization improves flexibility and isolation, but concentration means one privileged layer can create a very large blast radius. Virtual machine escape occurs when code inside a guest crosses the intended isolation boundary and gains access to the hypervisor, host, or resources outside that virtual machine. From there, an attacker may threaten neighboring guests or the virtualization platform. Escape vulnerabilities are especially serious because tenants and workloads rely on the hypervisor to enforce separation. Reduce risk by patching the hypervisor, minimizing host software, using hardware-assisted virtualization protections, separating workloads according to sensitivity, restricting device pass-through, and monitoring unusual guest-to-host behavior. Strong management security also matters, although stolen administrator credentials are not the same as a technical escape. On the exam, look for the direction of movement. A normal compromise moves within the guest. Virtual machine escape moves from guest to host or hypervisor. Movement from the host into guests may involve management plane compromise instead. Do not confuse escape with virtual machine sprawl, which is uncontrolled growth of instances, or with resource exhaustion, where one workload consumes shared capacity. The defining clue is broken isolation between the guest and the virtualization layer. Resource reuse occurs when storage, memory, or another shared resource is reassigned without properly removing previous data. A new user or tenant may recover information left by the prior owner. Sanitization, encryption, secure deletion, memory clearing, and platform isolation reduce this risk. Cloud environments add vulnerabilities related to shared responsibility, rapid automation, internet-accessible services, and complex identity. Common examples include public storage, overly permissive identity policies, exposed access keys, insecure application programming interfaces, unprotected metadata services, weak tenant separation, and configuration drift. Cloud does not remove traditional vulnerabilities. It changes ownership and scale. The provider secures some layers, while the customer remains responsible for others according to the service model. Controls include least privileged identity, secure defaults, encryption, key management, continuous configuration monitoring, network restrictions, logging, and clear responsibility mapping. On the exam, determine whether the flaw is data residue from reused resources, a cloud misconfiguration, or a provider isolation failure. A public storage bucket is usually customer configuration. Cross-tenant leakage may indicate a shared platform or resource reuse issue. Identify who controls the vulnerable layer before selecting remediation.
Supply chain vulnerabilities arise when an organization inherits risk from a provider, product, component, or development dependency. Security boundaries extend beyond the company because trusted outsiders may hold administrative access, process sensitive data, deliver updates, or supply hardware. A weakness at one provider can affect many customers simultaneously. Reduce risk through due diligence, clear contract requirements, independent security evidence, least privileged partner access, segmentation, component inventories, signed artifacts, continuous monitoring, and coordinated incident response. Understand subcontractors as well as the primary vendor. Contracts should address notification, logging, vulnerability remediation, data handling, access termination, and audit rights. On the exam, look for the path of inherited trust. If multiple customers are compromised through one management platform, the provider relationship is central. If a vulnerable library appears in many products, the dependency is part of the software supply chain. Traditional controls still matter, but the organization may not directly control the vulnerable system. The correct response often combines provider governance with technical limits on what the provider can reach. Service providers and hardware providers create different supply chain exposures. A service provider may process data, host systems, monitor networks, or maintain remote administrative access. Compromised provider credentials or tools can give an attacker a trusted path into customer environments. Limit that path with strong authentication, least privilege, time-bound access, dedicated management networks, session recording, and rapid access removal. Hardware providers introduce risk through counterfeit components, insecure design, vulnerable firmware, hidden functions, tampering, or uncertain provenance. Use approved suppliers, chain of custody records, tamper evidence, component validation, firmware verification, and hardware attestation where appropriate. Maintain alternatives for critical components. On exam questions, identify what is being supplied. Remote support access points toward service provider risk. A manipulated component arriving before deployment points toward a hardware provider. A provider may be reputable and still become compromised, so reputation alone is not a control. Verify the product or access, restrict trust, monitor behavior, and prepare to isolate the relationship when indicators appear. Software provider risk spans the path from source code to the installed update. Attackers may compromise a developer account, third-party library, source repository, build runner, signing key, package registry, update server, or distribution network. The final software can appear legitimate because it comes through a trusted process. A software bill of materials helps identify included components when a dependency becomes vulnerable. Dependency scanning, protected branches, code review, isolated builds, least privileged automation, secret scanning, and hardened signing systems reduce risk. Reproducible builds can help verify that source produces the expected artifact. Customers should validate signatures, test updates in stages, monitor behavior, and preserve rollback capability. On the exam, distinguish a malicious update from an ordinary unpatched application. A malicious update delivers harmful code through the trusted channel. A vulnerable dependency introduces a flaw that may later be exploited. Both are software supply chain issues, but their immediate mechanisms differ. Protect every link, because a secure application can still be undermined by one untrusted component or compromised release process. Cryptographic vulnerabilities occur when algorithms, keys, parameters, random values, protocols, or implementations fail to provide the expected protection. Examples include obsolete algorithms, short keys, predictable random number generation, nonce reuse, exposed private keys, incorrect certificate validation, weak protocol negotiation, and side channel leakage.
Strong algorithm names do not guarantee strong security. Encryption can fail when keys are stored beside the data, reused too long, or generated predictably. Use approved modern algorithms, sufficient key lengths, secure random generation, unique nonces, authenticated encryption, protected key storage, rotation, revocation, and correct certificate validation. Hardware security modules can protect high-value keys and perform operations without exposing private material. Patch cryptographic libraries and disable legacy protocols or downgrade paths. On the exam, identify the failed property. An exposed key is key management failure. Repeating a nonce can break an otherwise strong mode. Accepting an invalid certificate is trust validation failure. Choosing a deprecated hash or cipher is algorithm selection. Fix the cryptographic design or implementation rather than simply adding more encryption around the same weakness.
Misconfiguration occurs when technology is deployed with unsafe settings, even though the underlying product may function correctly. Common examples include public cloud storage, excessive permissions, default accounts, exposed management interfaces, overly broad firewall rules, disabled logging, insecure security groups, weak access controls, and unnecessary services. Misconfiguration is common because modern environments contain many settings, rapid changes, and overlapping administrators. Reduce risk with secure baselines, hardened templates, infrastructure as code, peer review, automated policy checks, configuration changes, continuous drift detection. Defaults should be secure, and exceptions should have owners and expiration dates. Testing must examine effective access, not only the intended design. On the exam, distinguish misconfiguration from a software defect. If an administrator makes a private data store public, the weakness is configuration. If correctly configured software still mishandles memory, the weakness is code. The direct mitigation is to correct the setting and then verify that exposure has been removed. Patching may still be useful, but it does not automatically repair unsafe permissions or architecture. Sideloading installs a mobile application from outside the approved application store or enterprise distribution channel. It may be legitimate for testing or internal deployment, but it bypasses some review, reputation, and update controls. Attackers distribute modified or counterfeit applications through websites, messages, third-party stores, and shared files. The application may request excessive permissions, steal credentials, monitor communications, or avoid normal update mechanisms. Controls include mobile device management, application allow listing, enterprise app stores, signed packages, device compliance rules, and policies that block installation from unknown sources. Verify developer identity and package signatures. Keep applications and the mobile operating system updated. On the exam, focus on the distribution path. Installing an application package directly instead of using an authorized store is sideloading. The device does not have to be jailbroken for sideloading to occur, although platform restrictions vary. A malicious app from an official store is a different review failure. Sideloading specifically describes bypassing the approved delivery channel, which increases uncertainty about origin, integrity, permissions, and updates. Jailbreaking or rooting removes or bypasses vendor-enforced security restrictions on a mobile device. The process grants elevated control, allows unauthorized modifications, and may disable code signing, sandboxing, integrity, or update protections. Users may jailbreak a device for customization, but the change expands the attack surface and reduces confidence in device state. Malicious applications can gain broader access, security tools may be bypassed, and official updates may fail or be delayed. Enterprise controls include mobile device management, device attestation, compliance checks, conditional access, application restrictions, and blocking compromised devices from sensitive resources. Restore the device to a trusted, vendor-supported state when possible. On the exam, distinguish jailbreaking from sideloading. Sideloading installs an app outside the approved store. Jailbreaking changes the platform's security boundaries and privilege model. A device can sometimes sideload without being jailbroken. Look for clues such as root access, removed sandbox restrictions, modified system files, or failed integrity checks. The mitigation is not merely deleting one app. The platform must return to a known, trusted state. A zero-day vulnerability is a flaw that defenders or the vendor do not yet know about, or for which an effective patch is not yet available. A zero-day exploit is the technique that abuses that flaw. The term describes knowledge and remediation timing, not severity. Some zero days are extremely dangerous, while others have limited impact or difficult prerequisites. Because signature-based defenses may not recognize a new exploit, defense in depth matters. Use least privilege, segmentation, application control, behavior-based detection, exploit mitigations, secure configuration, isolation, threat intelligence, and rapid incident response. A web application firewall or intrusion prevention rule may provide virtual patching until a vendor fix arrives. When a patch is released, test and deploy it according to risk. On the exam, distinguish zero-day from an old, unpatched vulnerability. If a patch has existed for months but the organization did not install it, the issue is patch management. If exploitation occurs before a fix is available, zero-day is appropriate. Focus on reducing exposure and impact while monitoring for vendor guidance and indicators. Effective vulnerability mitigation follows a life cycle. Discover assets and weaknesses through inventory, scanning, testing, code review, threat intelligence, and reports. Validate findings so false positives do not consume resources. Classify the vulnerable layer and determine exposure. Prioritize using exploitability, active exploitation, asset criticality, data sensitivity, business impact, and available controls. Remediation may involve patching, secure configuration, code changes, isolation, access restriction, compensating controls, migration, or replacement. Assign an owner and deadline. After remediation, verify that the weakness and exposure are actually reduced. A successful patch installation message is not enough if the vulnerable service remains active or the system failed to update. Monitor for recurrence and configuration drift. Document accepted risk with rationale, authority, and expiration. On the exam, choose the control that addresses the root weakness. Patch known software defects. Parameterize database queries. Replace end-of-life hardware. Correct public permissions. Isolate unavoidable legacy systems. Defense in depth remains valuable, but direct remediation should be preferred when feasible and safe. Finish Objective 2.3 with a 4-step decision process. First, identify the vulnerable layer: application, operating system, web, hardware, firmware, virtualization, cloud, supply chain, cryptography, configuration, mobile, or unknown zero-day. Second, identify the condition. Is input changing an interpreter command? Is memory exceeding a boundary? Is state changing between check and use? Is trust inherited from a provider? Is a setting exposing data? Third, predict impact, such as code execution, privilege escalation, data disclosure, cross-tenant access, persistence, or service failure. Fourth, select the direct mitigation. Use parameterized queries for SQL injection, output encoding for cross-site scripting, synchronization for races, signed protected updates for release chains, hypervisor patching for virtual machine escape, secure key management for cryptographic risk, mobile compliance for jailbroken devices, and defense in depth for 0 days. Read the whole scenario. A technique may cross several layers, but the question usually provides one decisive clue. Remember the formula: layer, weakness, impact, and mitigation. With that structure, you can compare answer choices and choose the most specific supported response.